Hi everyone, welcome to today's lesson on measurement and uncertainty. In this lesson, we are going to learn about a few things that are important in our labs. We're going to talk about why accuracy and precision are important, and then the uncertainty in our measurements. So in labs, when we make measurements and perform calculations with our measurements, there are a few things to consider in this entire process. The first thing we want to consider is the instrument itself. There are two things we want to keep in mind when we choose our instruments: accuracy and precision. And so accuracy is about the measurement and whether it is close to the correct or accepted value. Accuracy means how good our instrument is at getting the most accurate results. The process of adjusting our instruments to make it accurate is called calibration. Okay, so measurements, once again, it is about how close to the correct or accepted value. On the other hand, precision means a reproducible measurement or a measurement with more significant digits. Precision means how many significant figures. A good working instrument will give us a good number of significant figures, usually at least 4. And so we'll look at significant figures in the next lesson. High precision also means that if we use the instrument again, we would get the same results or results that are close to the first result. And so let's take a look at these 4 target boards here. If we're looking at kind of a person throwing darts here with kind of 4 different results or 4 different throwers. And so if we take a look at kind of the first board here, you'll notice that these darts, they're not very grouped together. Okay, and compared to thrower B here, all 4 darts are kind of in the same region. So we would say that thrower B is more precise. And likewise, D is probably a little bit more precise as well. C, the darts are still all over the place. Now, when we're looking at who's the most accurate thrower, we would say D is the most accurate thrower because all of D's darts are centered in the middle of the target board. And so the most accurate throws are from thrower D. The most precise throws are from thrower B and D. In other words, if we had to choose one of these throwers to be on our team, we would definitely want thrower D because thrower D here is both accurate and precise. Another example here, let's say we have a weight that has a mass of exactly 1.000000 grams. A student uses 4 different balances to check the mass of the weight, and the results are shown below. Mass using balance A is 0.999999 grams. Mass using balance B is 1.00 grams. Mass using balance C is 3.0 grams. And then mass using balance D is 0.811592. So if we're looking at these 4 balances, the balances that give us the most accurate measurements are balances A and B. C is pretty off. D is close, but still a little bit off. In terms of which balances gives us the most precise measurements, in this case, we're trying to see which of these scales will have kind of the most significant digits or digits. And so this would be balance A and balance D, as they give us a lot of these decimal places. And so if we were to kind of choose the balance that gives us the most accurate and precise measurements, this would be A, because A is both accurate and precise. Another thing that we kind of look at when we're doing labs is this term here called uncertainty. When we're counting, it is easy to be exact. For example, there are 30 students in the class. All we have to do is count. However, when we're measuring properties such as mass, volume, and time, it is harder to find the exact value. This is called an uncertainty. Therefore, once we have picked the most accurate and precise equipment or instrument, we want to be cautious and aware of our measurements and its uncertainty. For example, looking at the measurement to the right, we can accurately say that the liquid level is between 42 and 43. Okay, so if we look at this liquid level, it is definitely somewhere between 42 and 43, but we cannot say for certain where in between 42 and 43. And so my guess here would be 42.6 millimeters. Now, someone else might have a 42.7 milliliters, or another person might have 42.8 or 42.5 milliliters. And so when we look at this measurement here, 42.6, the 42, this is what we call a certain digit. Certain digits are measurements that you are 100% sure of. Like we are 100% sure that it's somewhere between 42 and 43. However, this last digit here, the 6, this is our uncertain digit because this is the digit that we had to guess or estimate based on the measuring instrument used, right? Someone could have 42.7 or 42.8 or 42.5. And so that's the last digit. That's the uncertain digit. And so from the measurement above, the certain digits are 42, while the 6 at the end is the uncertain digit. Let's take a look at the following examples. Imagine that this is a ruler. So let's take a look at value 1. Okay, so if I'm trying to decipher this ruler here, I have 6.2, this is 6.21, 6.22, 2, 3, 4, 5, good. Okay, so that means that this value here has to be somewhere between 6.21 and 6.22. I'm going to make a guess of 4. Okay, so that's the uncertainty or the uncertain digits, that 4 at the end. Okay, B, what is the value at 2? Okay, so if this is 6.25, this is 6.26. Okay, so I'm going to guess maybe 6.26. Okay, that's my certain digits, maybe 3. Okay, at value 3, I think it's pretty kind of close to here. I'm going to guess this is 6.3. Okay. Now, another thing about uncertainty is this experimental uncertainty. And this is the estimated amount by which a measurement might be in error of. Okay, so for example, if I take a look at the following number at 39.6 plus or minus 0.1 degrees, this means with that plus or minus 0.1 degrees that the actual temperature could be somewhere between the low end, so 39.6 minus 1, 39.5, or on the high end, 39.6 plus 0.1, so 39.7. Okay, so that number there, 39.6 plus or minus or 0.1, that gives me kind of the range of my actual measurements. And so if we wanted to calculate experimental uncertainty, all we have to do is we multiply the smallest unnumbered subdivision or the smallest increment by 0.1. Okay, let's take a look. So if I'm making this measurement here, I have 2. This is probably 2.2, 2.4, 2.6, 2.8, and then 3. So I'm going to make my guess that this is 2.27. So that's my guess. Once again, the last digit is our uncertain digit. Now, if I take a look at my smallest increment is 0.2. So I take my smallest increment and I'm going to multiply it by 0.1, and that gives me 0.02. And so this is going to be my experimental uncertainty, meaning that after I make my measurement 2.27, okay, I can add in my experimental uncertainty 0.02, and that would tell me that my measurement there could be off by positive 0.02 or minus 0.02. Let's try another question here. This is 6.2, 6.21, 6.22, 6.23. Okay, so that means my measurement here is somewhere between 6.22 and 6.23. I'm going to make a guess 6.226. Once again, we can figure out the experimental uncertainty by taking the smallest increment. And this smallest increment is 0.01. We multiply by 0.1 to give us plus or minus 0.001. And so that's my uncertainty, plus or minus 0.001. Something about kind of our experimental uncertainty and measured value. And that is we always want to make sure, however many decimal places we have in our uncertainty, experimental uncertainty, we want to match that in our actual number. Okay, so let's write that down. Make sure the decimal places in the experimental uncertainty matches that of the measurement. Okay, so let's double check. Here I have 2 decimal places, 2 decimal places, so I'm okay. Now if I go back a little bit to this example here, you'll notice that in A I had 6.214, in B 6.263, C 6.3, and it ends there. But if I take a look at the smallest increment here, this is 0.01. Okay. In other words, if I multiply by 0.1, my experimental uncertainty is going to be plus or minus 0.001. And so if I'm adding my experimental uncertainty, then I need to make sure that if I have 3 decimal places, that this also has 1, 2, 3 decimal places. So always make sure that your experimental uncertainty matches that of your actual measurement. Let's take a look at another example here on reading the burette or the graduated cylinder. For all these instruments, if the space is quite narrow, water often forms a bend. We call that a meniscus. And so when we're using these glassware, we want to make sure that when we're making or reading our measurements, we read from the bottom of the meniscus for the most accurate measurements. Okay, so let's record the measurements with the correct number of digits and then report the uncertainty of the reading as well. Okay, so example 1 here, this is 36.6. Okay, smallest increment is a 1 times 0.1. So this is plus or minus 0.1. Here we have 2, 4, 6, somewhere between, I'm going to say 7.1. Smallest increment is a 2 times 0.1 equals 0.2 plus or minus 0.2. Decimals check out. Now 13, this is 13 or 12. Somewhere between 12 and 13, I'm going to say 12.2. Once again, or I'm just, yeah, it's 12.2. Once again, my increment here is 0.2 times 0.1, 0.02. And so because my experimental uncertainty has 2 decimal places, I want to make sure that my answer here also has 2 decimal places. Final row here, 5, 6, 7, 8, 9. So 9, this smallest increment is a 1 times 0.1. 0.1, so plus or minus 0.1. Since there's 1 decimal places, I want to make sure my measurement also has 1 decimal places. Then this is 7.15. Okay, let's double check. This is 0.1 times 0.1 equals 0.01. So our measurement needs to have 2 decimal places, which it does. Okay, so that matches up. This is 60, maybe 60.3. Okay, decimal, or let's take a look at the decimal places. The smallest increment, this is 0.1 times 0.1 equals 0.01, and therefore the uncertainty is 0.01, 2 decimal places, so this is going to be 60.30. As always, please make sure you try the fun sheets and then check your answers with the fun sheets, and then email me if there are any errors or if you have any questions. See you all next time.